So, in the previous lecture we were discussing about the volumetric strain as an important parameter, but we also started discussing about the angular strain, and this in a simple way schematically represents that what are the features in the angular strain that we are looking for. So, we will try to quantify this. Let us say that delta x is the length along x and delta y is the length along y. So, now we will try to find out this angle delta alpha and delta beta. So, to do that what we will do is we will make this construction, we will construct a right angle triangle here. So, this distance is what? So, if v is the velocity here over a time delta t, this goes up by v into delta t. If the velocity here is v, the velocity here is this is not del v del y, because from here to here when there is a change in v, that is change in v due to moving along x and not along y. So, v plus del v del x into delta x plus higher order terms into delta t. So, what is this much? This much is the difference between these two. And what is this much? This is delta x plus higher order terms, delta x plus the change along x. So, we can write from this right angle triangle that tan of delta alpha as delta t tends to 0, delta alpha will also not be large. So, we can say that tan of delta alpha is same as delta alpha. So, as delta t tends to 0, tan of delta alpha tends to delta alpha. So, you can write limit as delta t tends to 0, delta alpha, here it will become delta alpha divided by delta t is equal to del v del x, or this rate of change of angle alpha, alpha dot is del v del x. Similarly, beta dot will be del u del y. Now, the big question is, what is the rate of deformation? So, the rate of deformation or rate of shear strain, these are synonymous terms. Is the rate of change of the angle between two line elements by definition which were perpendicular to each other. So, this is the definition. So, these two line elements, they were originally perpendicular to each other. Now, the angle between these two line elements is this. What is this? Pi by 2 minus delta alpha minus delta beta. So, what is the change in angle between these two? Delta alpha plus delta beta. What is the rate of change of that? That is alpha dot plus beta dot. So, that is del V del x plus del U del y. For a flow where V is not there, the rate of deformation is simply del U del y. That is how in the Newton's law of viscosity that you have learnt in a first level course of fluid mechanics, the shear stress will be related to del U del y for a case where there is no V, otherwise it is a combination of these two. The next definition is angular velocity. In the xy plane, the angular velocity component is with respect to z axis. What is that? The angular velocity with respect to z axis is essentially the average of the angular velocity, how it is defined, of the two line elements that were perpendicular to each other. So, this line element according to the schematic is shown to move in the anti-clockwise direction. So, it is positive, and this line element according to the schematic is shown to move in the clockwise direction. So, that is negative. So, this is half of alpha dot minus beta dot. So, this is half of So, we have introduced two important definitions, one is rate of deformation, another is angular velocity with respect to a particular axis. Now, this angular velocity is related to a mathematical quantity which is defined as vorticity. So, vorticity this is defined as curl of the velocity vector. So, in a determinant form, so if you call the vorticity vector as capital omega, so very interestingly you see that this is physically 2 into the angular velocity with respect to the z axis. Similarly, this is 2 into angular velocity with respect to x axis, and this is 2 into angular velocity with respect to y axis. So, the vorticity vector is physically twice the angular velocity vector. So, vorticity physically means rotationality in the flow, and the rotational elements in the flow are called as vortices. So, there are situations when there is no rotationality in the flow, and that is called as irrotational flow. So, irrotational flow the vorticity vector is a null vector, there is no rotationality in the flow. So, now we will consider some special kinematic situations. The first case is two dimensional incompressible flow. So, two dimensional incompressible flow means this one. So, in the two dimensional incompressible flow you have a single equation with parameters, two parameters u and v. Can you boil down these to a single parameter? It is possible. Say you define u is equal to, where this psi is a function of x and y, this plus or minus sign with u and v, one has to be opposite to the other. So, you could as well define u is equal to minus del psi del y and v is equal to plus del psi del x. So, they have to be opposite because sum total has to be 0. So, if you put this here, it will, you will see that it trivially satisfies the two dimensional incompressibility condition. So, this psi is called as stream function, which is a function of x y. So, this stream function STREAM, stream function. Now, the question is that why out of so many names it is called as stream function? What is so special about it? Well, the answer is quite straightforward. So, you find out the condition of d psi equal to 0 or psi equal to constant. So, d psi is a function of x and y. So, by the rule of partial derivatives, so now you see the definition, u is equal to del psi del y and v is equal to minus del psi del x. So, this becomes dx by u is equal to dy by v. This is equation of streamline. This is equation of streamline, and we have just seen that for a streamline you have psi equal to constant. So, psi equal to constant essentially represents a streamline, but you have to remember one thing, this analogy is there only for two dimensional incompressible flow. For all types of flows you will have streamlines, but for all types of flows you do not have the stream function defined. Stream function is defined only for two dimensional incompressible flow. So, only for such cases you will have this analogy between stream function and streamline, that is the constant stream function represents a streamline. Okay. Let us consider a case 2 which is irrotational flow. Already we have defined what is irrotational flow, and there is an important vector identity. This is a vector identity. Curl of gradient of a scalar is a null vector. So, if you compare this with this, essentially for irrotational flow we can write V as a gradient of a scalar variable phi. This is a function of x, y and z because it is a in general a 3-dimensional parameter. So, the corresponding scalar components are u is equal to del phi del x, v is equal to del phi del y and w equal to del phi del z. So, this velocity potential is physically reminiscent of an irrotational flow. So, if this is defined or this exists only if the flow is irrotational, and an irrotational flow will remain irrotational forever if there are certain effects which are absent, and one of such effects is viscosity, because viscosity can bring rotationality in the flow. How it can do that we will see later on, but one of the interesting things is that if the flow is both inviscid and irrotational, it will remain irrotational forever, and that means the velocity potential is always defined at all times, and such a flow is called as potential flow. So, inviscid irrotational flow is called as potential flow, and we will discuss about that in details in one of our later chapters. So, now we have considered two special cases. One is 2-dimensional incompressible flow where the parameter defined is psi. In case of irrotational flow the parameter defined is phi. The objective is very similar, that you have to, there are too many unknowns, you reduce all those unknowns in the form of a single parameter. Now, can there be situations when both phi and psi are defined? Psi is defined for 2-dimensional incompressible flow, phi is defined for any rotational flow, maybe 2D or 3D. So, their intersection when both of them are defined is for 2-dimensional incompressible and irrotational flow. So, let us discuss that. Consider 2-dimensional plus incompressible plus irrotational flow. So, then both phi and psi are defined. So, now you can write d psi this we have already written. So, this is u, this is minus v. So, psi equal to constant or equivalently d psi equal to 0 will lead to dy dx for psi equal to constant. So, you just write dy dx is equal to v by u. For 2-dimensional irrotational flow, phi is a function of x and y, it is no more a function of the third variable. So, d phi so this is by definition u and this is by definition v. So, phi equal to constant or d phi equal to 0, this will mean dy dx for phi equal to constant as minus u by v. So, at a common point when you have phi equal to constant lines, these are imaginary lines, and psi equal to constant lines. So, dy dx for phi equal to constant multiplied by dy dx for psi equal to constant is equal to v by u into minus u by v. This is minus 1 provided you can do this multiplication and cancellation if u v are not equal to 0, this is very important. So, if u and v are not equal to 0, you can cancel all this and then basically this product of these two is minus 1. What does it mean? So, if you have phi equal to constant lines and say let us say these are phi equal to constant lines, say phi equal to C1, phi equal to C2, phi equal to C3, and let us say these are psi equal to constant lines, psi equal to K1, psi equal to K2, psi equal to K3. Then if you find out say a common point of intersection, dy dx to this essentially means the slope of the tangent. So, you draw the tangents and because the product of the slope is minus 1, that means their tangents are actually perpendicular to each other. That means they are called as orthogonal set of lines, that their common tangents are perpendicular to each other. So, when that occurs, that is there provided that u v are not 0. If u and v are 0, then such a point is called as stagnation point. So, at the stagnation point you do not have this kind of interpretation, because at the stagnation point you really cannot cancel u and v. So, stagnation point is a point where the velocity comes to a standstill, that is the velocity is 0. So, this kind of network structure where you have this phi equal to constant lines and psi equal to constant lines, set of orthogonal lines, this is a kind of network also equivalently a flow network or flow net. The other point about this phi and psi is, so let us consider the definition of psi. So, u is equal to del psi del y and v is equal to minus del psi del x. So, now if you recall that we have considered two dimensional incompressible and irrotational flow in this example. So, if it is irrotational, so this is two dimensional plus incompressible. If it is irrotational, then what is this? So, what it essentially means is so in the two dimensional situation, this is nothing but the Laplacian operator for two dimensional. Similarly, for irrotational flow, for two dimensional and incompressible flow, you have so that means you have or in other words so interestingly both phi and psi when they are defined simultaneously, that is two dimensional incompressible and irrotational flow, they will satisfy the Laplace equation. Of course, their solutions will be different because their boundary conditions are different, but their solutions will be orthogonal in the space, and therefore solving these two equations will give you orthogonal sets of lines. So, physically where the stream function will be important for analysis, it will be important when you are trying to reduce the parameter for an two dimensional incompressible flow from two parameters essentially to one, or for irrotational flow no matter 1D, no matter 2D or 3D, you are interested to convert it from the velocity space to a single parameter phi, which is the velocity potential space. So, that may help you to write your governing equations in terms of these parameters either phi or psi. So, to summarize, we have made a brief recapitulation of fluid kinematics through the first 5 modules in particular of this online course on advanced fluid mechanics. The whole idea is not really to get into details of all the features of fluid kinematics, most of which have been discussed in the first level course of fluid mechanics, but to give you a perspective of the conceptual foundation and conceptual understanding of how to describe fluid motion in terms of velocity, acceleration, deformation, and what are the essential implications and what are the conceptual paradigms. Based on these concepts, we will take it further forward and we will study further the dynamics of inviscid and viscous flows, where the objective will be eventually to relate the force with the deformation, and for viscous flows the force deformation relationship will eventually make us arrive at the famous equation of motion, which for a very special case boils down to the Navier-Stokes equation. So, through these initial 5 lectures I have tried to build up a basic platform or a basic foundation through which we can move further forward towards learning more advanced concepts in fluid mechanics. Thank you very much.